Hello and welcome. Today we are going to begin a gentle journey into the world of mathematics, specifically focusing on the concept of sets. This is part one of a four-part series on representing sets. In this video, we will start at the very beginning by answering a fundamental question: what exactly is a set? We will look at clear definitions, understand how membership works within a set, and finally, take a brief overview of the topics we will cover in the future. Let's get started. Let us start with a simple question: what is a set? The formal definition tells us that a set is a well-defined collection of distinct objects. Let's pause and think about those words carefully. Well-defined means there is absolutely no confusion about what belongs in the collection and what does not. Distinct means that every object in the collection is completely unique. The individual objects that make up the set are called the elements, or sometimes they are referred to as the members of the set. To make this easier to visualize, try to think of a set as a simple bag. In this analogy, the bag itself represents the set. The items you place inside the bag are the elements. There are two very important rules to remember here. First, each item appears only once inside the bag. There are no duplicates in a set. Second, the order in which you put the items into the bag does not matter at all. As long as the items are inside, it is exactly the same set. Let's look at some everyday analogies to make this perfectly clear. If our set is a bag of fruits, the elements inside could be an apple, a banana, and a mango. If our set represents your class, the elements are the individual students, like Alice, Bob, Carol, and so on. If the set is the days of the week, the elements are Monday, Tuesday, continuing all the way through Sunday. And finally, if our set is the planets in our solar system, the elements would be Mercury, Venus, and the rest of the planets leading up to Neptune. Now that we know what a set is, let us learn how we write about them. We use special notation, specifically membership symbols, to show whether something belongs to a set or whether it does not. Let us use a running example to see how this works. Let us say we have a set called capital A. We will define set A as containing the numbers 1, 3, 5, and 7. This is simply the set of odd numbers that are less than 8. Now look at the first symbol on the screen. It looks a bit like a curved lowercase letter e. This symbol means is an element of. So looking at our example, we can write the number 3 followed by this symbol followed by capital A. We read this out loud as 3 is an element of A, or simply 3 is in A. And looking at our set, we can clearly see that the number 3 is indeed right there inside it. But what if a number is not in the set? Then we take that same curved symbol and draw a slash right through it. This symbol means is not an element of. For example, we can write the number 4, followed by this crossed out symbol, followed by capital A. We read this calmly as 4 is not an element of A. And if we look back at set A, we see only 1, 3, 5, and 7. The number 4 is nowhere to be found, so this statement is true. Let us look at another quick example, this time using words instead of numbers. Let's create a set called capital F, which contains exactly 3 fruits: an apple, a banana, and a mango. Because the apple is in the set, we can write apple, then the element of symbol, and then capital F. Apple is an element of F. However, a grape is not in our set, so we write grape, the crossed out symbol, and capital F. Grape is not an element of F. As we move forward in our studies, we will find that there are several different ways to write down or represent a set. Before we finish today, let us take a quick overview of the 4 main ways to represent a set. Think of this as a roadmap for what we will be learning in our upcoming lessons. The first method is called the roster or tabular method. The key idea here is simply to list every single element out one by one. This method is best used for small, finite sets, where you can easily write everything down without it taking too much time.
The second method is the descriptive method. Instead of listing individual items, the key idea is to describe the set using words. This is a very natural and flexible method, and it is best used for almost any kind of set. The third method is called set builder notation. Here, instead of listing items or using plain sentences, we write a specific mathematical rule that defines what belongs in the set. This method is incredibly powerful, and it is best used for very large sets or even infinite sets where listing every single item would be completely impossible. And finally, the fourth method is the Venn diagram. The key idea here is to draw a picture to represent the sets. This beautiful visual method is absolutely the best way for showing the relationships between different sets. Please do not worry if these sound a little complicated right now. In our upcoming videos, we will take our time, step by step, and study each one of these methods carefully. We will go through lots of examples together to make sure everything is perfectly clear.
In Part 2, we will be exploring two very common methods, the roster form, which involves listing, and the descriptive form, which involves describing. Let's take our time and walk through these step by step. Let's start with our very first method. It is called the roster form, though you might sometimes hear it called the tabular form. So, what is the roster form? The definition is quite straightforward. To write a set in roster form, you simply list all the elements of the set inside a pair of curly braces. You then separate each element from the next using a comma. There are two golden rules to remember here. First, the order in which you list the elements does not matter at all. And second, no element is ever repeated. Once an item is in the set, it's in the set. If we look at the template, we see a capital letter A representing the name of the set, an equal sign, and then our curly braces holding element 1, element 2, element 3, and so on. Let's look at some examples to make this perfectly clear. Our first set is named capital V. V equals the set containing A, E, I, O, U. As you might have guessed, this is the set of vowels in the English alphabet. Next, we have set P. P equals the set containing 2, 3, 5, 7. These are the prime numbers that are less than 10. Then we have set D. D equals the set containing 1, 2, 3, 4, 6, and 12. These are all the whole numbers that divide evenly into 12, known as the divisors of 12. Finally, we have set C. C equals the set containing the words red, green, and blue. These are the primary colors of light. Notice how in every example we use the curly braces and we separate our items with commas. Now let's look a little deeper into the roster form. Sometimes sets have a specific number of items, which we call finite sets, and sometimes they go on forever, which we call infinite sets. Let's look at set M. M is the set containing 1, 2, then we see 3 little dots, and then the number 12. Those 3 little dots are called an ellipsis. They just mean to continue the pattern. So this set is actually 1, 2, 3, 4, all the way up to 12. This is a shorter way to write the numbered months of the year. Next is set O, which contains 1, 3, 5, 7, and 9. These are the odd single digits. This is another finite set, meaning it has an end. But what about set N? N contains 1, 2, 3, and then an ellipsis, but there is no ending number. This means the pattern continues forever. This is the set of natural numbers, and it is an infinite set. Now let's look at the right side of the screen at some important pitfalls or common mistakes to avoid. Remember our rules from the last slide? First, duplicates are completely ignored. If someone writes the set 1, 2, 2, 3, that is exactly the same as just writing the set 1, 2, 3. The extra 2 doesn't change the set. Second, the order does not matter. The set containing 3, 1, and 2 is perfectly identical to the set containing 1, 2, and 3. They hold the exact same elements. And finally, as we just saw, remember to use the ellipsis, those 3 little dots, for very large or infinite sets. For example, set E equals 2, 4, 6, ... This clearly shows us the infinite set of all even numbers. We are now ready to move on to our second method of writing sets. This is called the descriptive form, or sometimes the statement form. If the roster form was all about making lists, the descriptive form is all about using words. By definition, you describe the set in plain English. You use a sentence or a phrase that clearly and perfectly identifies every single element that belongs inside that set. The general template looks like this. A equals the set of all, followed by your specific description. The easiest way to understand it is to compare it directly with the roster form we just learned. Let's look at the side-by-side comparison on the screen. On the left, we have the roster form, the set containing A, E, I, O, U. On the right, we have the descriptive form of that exact same set of all vowels in the English alphabet. It's just writing out the meaning in words. Let's look at the next one. The roster form is 2, 4, 6, 8, 10. The descriptive form is set of all even numbers from 2 to 10. For the third example, the roster form lists 1, 4, 9, 16, and 25. To write this in descriptive form, we say set of all perfect squares up to 25. And for our final example, we have the roster form 2, 3, 5, 7, 11, and then an ellipsis, indicating it goes on forever. Its descriptive form is simply set of all prime numbers. There is no need for dots here. The English phrase handles the concept of infinity for us perfectly. Let's look at a few more examples of the descriptive form, just to get completely comfortable with it. You could have the set of all planets in the solar system, or the set of all prime numbers. How about the set of all students in your class? You can also have the set of all countries in South Asia, the set of all odd natural numbers, or the set of all integers divisible by 5. As you can hear, these are just clear, everyday sentences. So when should we use this descriptive form instead of making a list? The descriptive form is wonderful to use when a set is very large or infinite. It is also the best choice when listing every single element is just too impractical or would take up too much space. Furthermore, it is excellent when you just want quick, easy communication with someone. However, this method does have one major limitation. Plain English can sometimes be a little ambiguous, meaning it could be interpreted in more than one way depending on who is reading it. Because mathematics requires absolute precision, we eventually need a method that combines the precision of math with the descriptive power of words. That method is called set builder notation, and that is exactly what we will be exploring in our next part.
In this third part, we are going to focus entirely on a concept known as set builder form. This is essentially a formal mathematical method for defining the rules that govern a set. Let's take our time to walk through exactly what this means, step by step. Something called the set builder form. This is essentially a mathematical way of writing rules for sets. Let's take our time, go step by step, and walk through exactly what this means. Let's begin with the definition. Method number 3 for representing sets is known as the set builder form, or sometimes simply the rule form. Instead of writing out every single element one by one like a grocery list, we specify a rule or a condition that every single element must satisfy in order to belong to the set. Instead of listing the elements, we describe the specific property that they must have. Let's look at the template for how we construct this. We use curly braces, just as we always do when talking about sets. We write a capital letter for the set name, such as A, followed by an equal sign. Then, inside the curly braces, we write a lowercase x, followed by a vertical line, and then a capital P with an X in parentheses. Occasionally, instead of a vertical line, you will see a colon used. Please know that both of these symbols mean the exact same thing in this context. Let's break down what these symbols actually mean. The lowercase x acts as a variable. It is simply a placeholder for any general element that might belong to our set. The vertical line, or the colon, is a very important mathematical symbol. It translates directly to the phrase, such that. Finally, the p of x represents the actual condition or rule that our variable x must satisfy to be included in the set. So when we put all of this together and read it out loud, we say the set of all x such that the condition p of x is true. Take a moment to let that sink in. We are building the set by describing the qualifications to get in. Before we look at more examples, it is incredibly helpful to know the standard sets of numbers. These are called common domains or universes. We use them all the time in set builder form to define what kind of numbers we are allowed to use. Let's review them gently. The symbol n stands for the natural numbers. These are our standard counting numbers, 1, 2, 3, 4, and so on. If we add a 0 subscript, creating n0, we mean the whole numbers. This simply takes our natural numbers and adds a 0 to the beginning, 0, 1, 2, 3, and so forth. The symbol z stands for integers. This group includes 0, all of our positive whole numbers, and all of our negative whole numbers, like -2, -1, 0, 1, 2, stretching endlessly in both directions. The symbol q stands for rational numbers. Think of these as fractions or decimals that either end or repeat in a pattern. Examples include 1/2, -3, or 0.75. Finally, the symbol r stands for real numbers. This is a very broad category that includes absolutely all the numbers on the continuous number line, even the messy ones that don't terminate or repeat, like the square root of 2, pi, the number e, alongside numbers like -5.3. Now let's see how we actually use these domains in practice. Look at our first example. Set A is the set of all x such that x belongs to the integers and x squared equals 4. Notice that little symbol that looks like a curved E. That means is an element of or belongs to. So we are looking for integers that when multiplied by themselves equal 4. There are only two numbers in the universe that fit both of those rules, -2 and +2. So if we were to write this in roster form, set A is just the set containing -2 and 2. Now let's look at set B. Set B is the set of all x such that x belongs to the real numbers and x squared equals -1. Let's think about this carefully. Is there any real number that gives a negative result when you square it? No, there isn't. Because there is no real solution to that equation, set B has no elements. It is an empty set, which we represent with the null symbol, a circle with a diagonal slash through it. Let's practice with some more basic examples to make this feel natural. Our first example is about even numbers. We can define set E as the set of all x such that x is an even natural number. If we wanted to write this out as a physical list, which is the roster form, we would write our curly braces containing 2, 4, 6, 8, and then a comma followed by 3 dots to show that this even pattern continues forever. Let's move to the second example, where we explicitly state a mathematical domain. We have set A. Set A is the set of all x such that x is an element of the natural numbers and x is less than 5. We know our natural numbers start at 1, so we're looking for basic counting numbers that are strictly smaller than 5. That makes our set very simple to list, just 1, 2, 3, and 4. In the third example, we're looking at divisors.
We define set D as the set of all x such that x is an element of the positive integers and x divides 12. Let's look closely at the notation here. Notice the symbol z with a little plus sign. That specifically means positive integers starting from 1. And that second vertical line sitting between the x and the 12 actually means divides. So we're asking what positive integers divide evenly into 12 without leaving a remainder. Those numbers are 1, 2, 3, 4, 6, and 12. So those numbers make up our set. To really solidify this entire concept, let's do a side-by-side comparison. Let's look at how the roster method and the set builder method described the exact same meaning, just in different ways. If we have the roster set containing 1, 3, 5, 7, and 9, how do we describe that in set builder form? We write the set of all x such that x is a natural number, x is odd, and x is less than 10. The meaning of both forms is simply odd natural numbers less than 10. Next, look at the roster set containing 0, 1, 4, 9, and 16. These are perfect squares. In set builder form, we can get a bit creative with our variable. We can write the set of all n squared such that n is a whole number and n is less than or equal to 4. This mathematically describes perfect squares less than or equal to 16. For the set containing -2, -1, 0, 1, and 2, our set builder form is the set of all x such that x is an integer and x is greater than or equal to -2 and less than or equal to +2. It's just the sequence of integers from -2 to 2. And remember, sets don't have to be strictly numbers. Look at the set containing a, e, I, o, and u. In set builder form, we can say the set of all x such that x is an element of the English alphabet and x is a vowel. We'll finish today by highlighting the true power of set builder form. While it might seem like a bit of extra mathematical writing for very small sets, its real strength is that it allows us to describe infinite sets concisely and elegantly. For example, we can say set P is the set of all x such that x belongs to the natural numbers and x is prime. That one short line of math perfectly captures an infinite number of prime numbers, beautifully contained in a single rule, without us ever having to write them all down.
In this part, we are going to explore our fourth and final method, Venn diagrams. After that, we will wrap things up with a nice summary, look at some special sets, and review everything we have learned so far. Take a deep breath, get comfortable, and let's begin. Up to this point, we have used words and symbols to represent sets. Now, we are going to use pictures. This brings us to Method 4, the Venn diagram. A Venn diagram is a wonderful visual tool that uses circles placed inside a rectangle to give us a picture of our sets. Let's break down what these shapes mean. The large rectangle represents our universal set, which we call U. You can think of this as the overall container for everything we are currently talking about. Inside this rectangle, we draw a circle. This circle represents one specific set. Let's call it set A. The rule for a Venn diagram is very simple. If an element belongs to set A, we draw it inside the circle. If an element does not belong to set A, we draw it outside the circle, but still inside the rectangle. Let's look at an example to make this perfectly clear. Let's say our universal set, U, contains all the whole numbers from 1 to 10. Now, let's say our set A contains just 3 specific numbers, 2, 3, and 5. If you look at the diagram, you will see exactly how this works. The numbers 2, 3, and 5 are placed safely inside the red circle because they belong to set A. Now, what about the rest of the numbers from 1 to 10? The numbers 1, 4, 6, 7, 8, 9, and 10 do not belong to set A. Therefore, they are placed outside the red circle. However, because they are still part of our universal set, they remain inside the purple rectangle.
It's a very clear visual way to separate what is in our set from what is not. Now, let's take a step forward and see what happens when we have two sets at the same time. Let's keep our universal set exactly the same, the numbers from 1 to 10. But now we have two different sets. Set A contains the even numbers 2, 4, 6, 8, and 10. Set B contains the numbers 1, 2, 3, 5, and 7. Notice that the number 2 is in both set A and set B. We call this the overlap. Because of this overlap, we draw our two circles so that they cross over each other in the middle. This creates 4 distinct spaces in our picture. Let's walk through them one by one. First, look at the left side, the red area that does not overlap. This is for elements that are only in set A and not in set B. Here we place 4, 6, 8, and 10. Next, look at the right side, the blue area that does not overlap. This is for elements that are only in set B and not in set A. Here we place 1, 3, 5, and 7. Now, look at that middle section where the red and blue circles cross. This is the overlap. Elements here must be in both set A and set B. The only number that fits this description is the number 2, so it goes right in the center. Finally, what about numbers that are in our universal set but are not in A and are not in B? They belong on the outside. Look around the empty space inside the rectangle. The number 9 isn't in set A and it isn't in set B, so it sits outside both circles. Now that we have learned all 4 ways to represent a set, let's look at a summary and put them side by side. Our first method was the roster method. This is where we simply list every element inside curly braces. For example, the set containing 2, 3, 5, and 7. We use this method when our set is relatively small and finite. Our second method was the descriptive method. This is where we just use a plain English sentence. For example, we could just say, primes less than 10. This is perfect for quick, everyday communication. Our third method was set builder notation. This uses a formal mathematical rule. It looks a bit more complex, reading as the set of all x such that x is a natural number, x is prime, and x is less than 10. We use this powerful method for very large or infinite sets where we couldn't possibly list everything out. And finally, our fourth method, the Venn diagram. This uses pictures of circles inside a rectangle. We use this when we really want to show the visual relationships between different sets, like we just did with the overlapping circles. Here is the most important key insight I want you to take away from this entire series. All 4 of these methods can describe the exact same set. They're just different languages. Writing the numbers 2, 3, 5, and 7 in brackets, saying primes below 10 out loud, writing out the formal set builder equation, or drawing a circle with those 4 numbers inside it, they all mean exactly the same thing. You are just choosing the best tool for the job. Before we move on to some practice, there are 2 special sets and 1 important concept that every beginner should know. The first is called the empty set. Just as the name implies, this is a set with absolutely no elements inside it at all. We represent it with a special symbol, a circle with a diagonal slash through it. You can also write it simply as a pair of empty curly braces. For example, the set of all human beings over 5,000 years old. Because no such human exists, that set is empty. Or, in mathematics, a real number whose square is -1. Since no real number can be squared to give a negative result, that set is also empty. A quick word of warning here. If you write curly braces and put the number 0 inside them, that is not an empty set. It is a set that contains 1 element, and that element happens to be the number 0. That leads us perfectly to our next special set, the Singleton set. A Singleton set is simply any set that contains exactly 1 element. For example, a set containing just the number 7, or a set containing just the number 0, or just the symbol pi. It doesn't even have to be numbers. The set containing our sun is a singleton set because there is exactly one element inside it. Finally, let's talk about the size of a set. In mathematics, we use a specific word for this, cardinality. Cardinality simply means the number of elements inside a set. To write this, we put straight vertical bars on either side of the set's name. So, vertical bar A, vertical bar, is read as the cardinality of set A. Let's look at some examples. If we have a set containing the vowels A, E, I, O, and U, its cardinality is 5 because there are 5 letters. What is the cardinality of the empty set? It's exactly 0 because there is nothing inside it. And what about the set of all natural numbers? Because numbers go on forever, its cardinality is infinity.
Now that we have covered all the theory together, it is time for some gentle practice. Let's look at 5 practice problems. I encourage you to pause the video here, take out a piece of paper, and try these on your own, at your own pace. When you are ready, press play, and we will go through the answers together. Let's carefully read through what we need to do. Problem 1 asks us to translate from the roster method to the descriptive method. We are given the set containing the numbers 3, 6, 9, 12, and 15. How would you describe this pattern in words? Problem 2 asks us to go backward, translating from the descriptive method to the roster method. The description is the set of all 2-digit perfect squares. We need to list those numbers out. Problem 3 takes us from set builder notation to the roster method. We have set A, which is defined as the set of all x, such that x is an element of the natural numbers, and x squared is less than 50. Problem 4 asks us to translate from the roster method back to set builder notation. We are given the simple set containing 0, 2, 4, 6, and 8. What is the mathematical rule for this set? Finally, problem 5 asks us to draw a Venn diagram. Our universal set, U, contains all the whole numbers from 1 to 8. Inside this universe, set A contains the numbers 2, 4, 6, and 8. Set B contains the numbers 1, 2, 3, and 4. Take your time, sketch your rectangle and your circles, and let's see how you do. Welcome back. Let's gently walk through the solutions for the first 4 problems. For problem 1, we needed to describe the numbers 3, 6, 9, 12, and 15. If you look closely, you will notice that these are all multiples of 3. They start at 3 and they stop at 15. So, using plain words, we can confidently say this is the set of all positive multiples of 3 that are less than or equal to 15. For problem 2, we needed to list all 2-digit perfect squares. A perfect square is just a number multiplied by itself. Let's count up. 3 squared is 9, which is only a single digit, so we skip it. 4 squared is 16. That works beautifully. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. And 9 squared is 81. If we go to 10 squared, we get 100, which is 3 digits, so we must stop there. Our roster set is simply 16, 25, 36, 49, 64, and 81. In problem 3, we needed to find all natural numbers whose square is less than 50. Starting from the number 1, we can square each number as we count up. 7 squared is 49, which is just under 50, so 7 is included. But 8 squared is 64, which is strictly greater than 50, so 8 is too big. Therefore, our set A contains the numbers 1, 2, 3, 4, 5, 6, and 7. For problem 4, we were looking at the numbers 0, 2, 4,
6, and 8. We can see they're even numbers, they start at 0, and they stop at 8. In set builder notation, we open our curly brackets and write the set of all x such that x is an element of n0, which means the natural numbers including 0, where x is even and x is less than or equal to 8. Now, let's look at the solution for problem 5, our Venn diagram. We start by drawing a nice large rectangle for our universal set U, which holds our numbers from 1 to 8. Inside, we draw two overlapping circles. The red circle is for set A, and the blue circle is for set B. Whenever you fill out a Venn diagram, the most peaceful place to start is right in the middle, at the overlap. Which numbers are in both set A and set B? Looking at our lists, both sets share the numbers 2 and 4. These are the even numbers that are also less than or equal to 4. So we place the 2 and the 4 right in that center intersection. Now let's look at the rest of set A, our red circle. Set A contains 2, 4, 6, and 8. Because we already placed the 2 and the 4 in the middle, we just need to place the remaining 6 and 8 in the left side of the red circle. These are numbers that are only in A. Next, we look at the rest of set B, the blue circle. Set B contains 1, 2, 3, and 4. Again, the 2 and 4 are already safely in the overlap, so we place the 1 and the 3 in the right side of the blue circle. These are the odd numbers that are only in B. Finally, we step back and check our universal set. We have placed the numbers 1, 2, 3, 4, 6, and 8. But our universal set contains all numbers up to 8. The numbers 5 and 7 are missing. They belong to our universe, but they are not in set A and they are not in set B. So they sit quietly on the outside of both circles, resting somewhere in the empty space of the rectangle. As we bring this 4-part series to a close, let's take a deep breath and review our key takeaways. First and foremost, remember that a set is simply a well-defined collection of distinct elements. Throughout this journey, we learned 4 beautiful ways to represent these collections. We learned the roster method, where we carefully list every single element inside curly braces. We explored the descriptive method, which allows us to simply say what the elements are using plain everyday words. We mastered set builder notation, giving us a formal mathematical way to write the rule for belonging to a set. And we just finished the Venn diagram, which provides a wonderful, easy-to-read visual picture using circles inside a rectangle. Always remember 2 golden rules when working with sets. In a mathematical set, order does not matter, and repetition is not allowed. Thank you so much for joining me on this gentle journey through representing sets. Coming up next time, we will expand our understanding as we explore subsets, power sets, and set operations. Until then, take care and happy learning. I am so very grateful for your kind support. It truly means the world to me. Please consider liking, sharing, and subscribing to join our gentle community, and I would truly love to hear your wonderful thoughts in the comments below.